I'm Dinulović from this perspective, professor at the Department of Aerospace. What I would like to present today are our generally recent achievements in the area of composites, actually core composites materials. The composites, not the only plates, but probably these ones where we actually use the honeycomb as a core for specific purposes, primarily in the aerospace industry. This is also related to some of our recent projects with the industry where we are actually trying to, first of all, deploy these kind of structures, second of all, to understand what's happening there and to try to model and to establish efficient methodology, especially for different types of dynamic analysis. That's one of the problems. The concept is not new. We are actually using that for quite some time, and here you can see some of general solutions what are applied actually today or general use in the aviation. This structure generally consists of core, which is of primary interest in our case with regular composite plates. And as I said, this concept is not new. However, methods for modeling these structures are actually in constant development. I will try to explain why and basically which and what actual problems are we facing at the moment for a particular problem that we have encountered in our line of work. Why are we, first of all, just brief explanation using this? Obviously, in aerospace applications, like in many other industries, but mass or weight actually is one of the biggest problems. With this kind of structures, you achieve, first of all, very great stiffness increase, strength increase with relatively acceptable weight penalties. This is why we use them, and this is how they generally work. These characteristics do not change linearly, but rather explicitly non-linear way to our benefit in terms of mass reduction or acceptable mass gain if you use force as a building block of your composite structure. That's one of the advantages. However, just basic how the composite plate with the core takes the load. Generally, the phase sheet that are on the top and on the bottom are responsible for carrying the direct, actually the normal stresses, where core mainly carries the shear stress. This will be very important at a later stage. Well, it really depends what you are trying to calculate, actually what you are trying to analyze. If you start with the I cannot say simple, but relatively static analysis. There are very well established methods here, different theories that are basically trying to transfer the real structure to something that we call the equivalent structure. This is done primarily because of the material complexity and second of all, the geometry complexity. And of course, this is all done in terms to recognize the elastic coefficient that we need in obviously the Fuchs law, the generalized Fuchs law. For this kind of structure, there are quite a few of these elastic coefficients that we really need to know in order to relate strains to stresses that all we do in also different kind of industry. But as I say, this approach is actually valid. I would say for a static analysis. Is it sorry? I didn't touch it.
Speak soft.
Yes, speak soft. Well,
You're scared.
So these are our, just to illustrate on this approach, this is our initial test that we've done, where we actually recognize that totally no linear behavior of our plates. And these models that were initially suggested by in literature are actually valid only in small, actually initial range. Let's say at point B, after that, nonlinearity occurs, and I don't know, collapse occurs, crashing occurs, and so on and so forth. What I'm trying to say is that these equivalent models are, as we say, beware of these, only good for a small or actually part of a region, the initial region. Perhaps dealing with the statics and in a linear domain, they're good because they're simple, they're efficient, they can be computed fast, and so on and so forth. But as soon as you try to switch to some other kind of non-linear analysis, dynamic analysis, all kind of fatigue analysis, this really won't do the work. So this is what we are actually trying to suggest, and we have experimented with this approach. To understand what I'm trying in the next few slides to explain is we really need to understand the manufacturing process of this honeycomb core. The starting point is actually paper, a really special kind of paper. There are 2 or 3 kinds, P14, P410, and the third one, to be honest, I forgot the trade name, but this is manufactured by DuPont. The key here is that already aramid fibers, which is very similar to Gel, is already embedded in this paper. Then this paper is dipped into a phenolic resin, not the epoxy, but phenolic, so becoming very, very interesting in our times. And then the forming of that paper is performed before we achieve this kind of hexagonal shape. How does that look? This is the paper, right? And from this dipped into phenolic resin, we obtain this kind of structure. What is important here to notice is that already the first initial stage, the paper itself is not isotopic, it is rather autotopic. This is also reported even by the manufacturer. We can see this here. If we look at these 2 numbers, this is the only paper that we see that Young's module here, E1, E2, are not the same, rendering the authenticity of this particular building compound. So that's why I say again, this is where starting these equivalent models already fail to predict for our more advanced analysis that we need. With phenolic, we don't have so much problem. It is considered to be isotropic, and there is no actual problem there. At the end, the structure really, at the cell level or representative volume element, really looks complicated from the material point of view, and then it looks complicated from the material point of view, as you have seen. So what we are trying here to suggest is to model not as the equivalent, but rather as it is. And at the bottom you can see the CAD model of this particular approach that we are trying to suggest, where we are trying to cell by cell to model the complete structure. Whereas you will see later in more detail the complete building block model like a composite plate that consists of the paper with its characteristics and with totally of the phenolic resin like it was built in a real way. This all cannot actually, because we have tried to work, and these are some of our experiments starting with dynamic analysis, with modeling certain structures with different approaches, when we actually discovered that these again equivalent models are not so precise. Actually, they do not render in dynamics any kind of result. Here you can see that the initial test for some specimens of some kind of wings. And the model analysis, actually the frequency response mode, the first 3 modes that we are trying to discover. The key is here. Just recently in literature, these results appeared by Roy et al. What they did in the lab conditions, first they took the paper itself, tested it, and then they took phenolic resin, tested it. Without these results, we actually will not be able, actually don't have these capacities here at the University of Melbourne, but the thing is, they did that and showed their results to the world and thank them, and I really thankful for this. Where you can see now the initial estimate on the paper level, you see it shows first of all very high nonlinearity. That's for one. On my right, on your left. Whereas the phenomenon as expected, so mild for specificity, but it's not so important as on the level of the data. So in our material model, we have actually used and programmed these particular graphs, which enable us further to enter the nonlinear zone of the core, like we had initially seen. Second of all, to pursue all other types of dynamic analysis that we are interested in. At the end, you will see the result. Again, there are very few papers regarding this approach. It depends again how you are going to model this RDE and what are going to be its material characteristics. We have adopted this particular one, which is somewhat the complex one compared to the previous ones. As I said initially, it is like a composite plate at the level of the cell of the core. Maybe it sounds complicated, and I would really say it is complicated for a human and for a computer as well. It would be nice, but we didn't do that. I don't know if you noticed at the beginning when I was showing you how the manufactured Nomex core looks like. Due to production reasons, you will always have the resin leftovers in the corners. At this stage of the analysis, we didn't take this into account, but unfortunately, it appears that they will have some impact on the final dynamic results. But this is left for some other and future, how shall I say, development of these models. So at the top now, one particular complete structure of interest. In our case, it's the aileron that we use on lifting surfaces. Relatively, it is of course approached by finite elements. And now you can see that here we have all implemented that we are actually, that I was talking about recently. At the level of the core, which is now modeled as a like a real structure, you will see it at the bottom, which is only one cell of the complete structure. Whereas within the cell, then you have a composite of itself. Based on these results, recently published in literature, the paper is modeled according to its experimental data, coupled with the phenolic resin with its, again, experimental data. Once we implemented that, then a real, or actually very well-known classical lamination theory would be deployed. So this is what we did, and now I hope that all kinds of analysis are now relatively, we are actually in position with this. Starting for a nonlinear static analysis, which you can see in the middle of the results of the shear stresses in the core. I would say actually it does make sense. First of all, nonlinear analysis at the level of the cell. Don't ask me how long the computer if it takes to compute, it's quite a long time. Second of all, there is quite a few geometric problems in red here. We'll pay attention. Even the walls of the Nomex core are not of the same thickness. At the level where they're actually during the conditional process, you would have thickness time too. So these are here shown in red. Third of all, another, I would say, a problem is that one, if accept this approach in this kind of precise modeling, at the mesoscale level should pay attention to really get to explore something that we call connections. Because here, first of all, we have the incompatible elements, we use 3D elements and plate elements. So this model is kind of full of connections. You can see them here in red. And these are not the blue connections, but rather linear collections in order to for this to work in the realm of the dynamic analysis. Nevertheless, we were chasing the first of all, the first two frequencies. The first one in twisting, actually in bending. This is the one where we can obtain. We're actually looking for this. I would say relatively complex model, creating the approach that I was actually explaining right now. To obtain the first frequency, which is the first dynamic analysis, that we always do the model analysis, coupled with, of course, chasing the next frequency, which is the frequency in torsion. This should be, I don't know, the next slide, but here it is. This is the first torsion frequency, but I think it's a fifth overall. I'm not sure. So first of all, we can say here how the structure together is working again. We have 3D elements here as the trailing edge that's shown in the black. Our Nomex scored in brown here. Attachments of the aluminum, again 3D. And then, of course, plates are thin composite plates. Interesting is to see the frequencies around the 1 kilohertz. That's on a similar structures, but rather single beams according to ASTM standard, were published, but just a simple beam, as I said. And the results are in the order of magnitude of this value. I was really surprised to see that it is there. One computer just died, calculating this, which is the good results. Right, yes, yeah. So now it's back because, of course, the power supply blew up. It was really, and it was +9. Just to give you an idea, and I think it takes up to 7 hours to calculate this. Nevertheless, in a conclusion, I would like to know a better or more efficient approach, which I think is a drawback and actually something that is not so good with what we are proposing. But I don't know for nothing better if you want to do the dynamics at the mesoscale levels. And if you have any ideas, I would really like to share it with you. And I don't know, keep a good eye on cooling your computers. That's all I can say. Thank you very much.